Okay, awesome. Now we can get started. So sorry for this small chaos. And hopefully we'll get this through for the rest of the course. All right, everybody. So today we're going to continue with the phase diagram, first of all. So you probably remember what we did yesterday. And we actually studied about diffusion. You remember, yeah, we wanted to study processes this week. And for the processes itself, we know for most of the, let's say, metal or metallic materials, we usually need to do a so-called solidification process and to get our materials into the composition that we want. That's why we need to understand what is happening basically during this solidification. So we're kind of converting our stuff from liquid to solid. This is already so-called phase transformation. And when you go to solid, the phase transformation actually does not stop there, right? There's even more complicated solid phase transformations are happening over there. That's why we're inventing, or we're kind of learning basically the phase diagram, to tackle this problem, because we want to know when we just go to a certain temperature or go to a, let's say, certain composition of your material, and what kind of phases are present, and what is the individual composition of each phase, and what are the fractions of all these phases. So that was basically, let's say, the motivation for us to learn all stuff, yeah. And yesterday we studied about unary phase diagram, basically. And we also studied about the binary phase diagram. Maybe you remember, we studied about this isomorphous binary diagram. Oh, the good thing to go with this is, I think everybody still says me, is you remember the binary isomorphous diagram, right? We could have, let's say, a complete solubility about two atoms. That was about copper and aluminum, I guess. Or no, maybe copper and silver, I guess. Yeah, aluminum cannot be fully dissolved into copper. Yeah, so that was the kind of isomorphous diagram. And today we're going to go to a little bit more complicated one, because that was really simple for a binary diagram, phase diagram. Today we're going to go a little bit more and more complicated, and say, let's say, the first more complicated one is so-called eutectic binary diagram. So if you know Greek, and probably you understand this name better. So eutectic is a basic combination of two Greek words. Yeah, the tectic in Greek means melt. Yeah, to melt something. So from solid to liquid. And EU doesn't mean Europe. Actually, it means well or easy. So basically, eutectic means something like easy to melt and melt easily, something like this. And how does it refer to a phase diagram looking like this to the right-hand side of the slide? And actually, the eutectic diagram is just referring to one point. So actually, it is referring to this point. Because if you just look at diagram, you always go with, heating or cooling. Let's go with the heating. So if you have a combination about copper and silver. Oh, this is silver. Okay, so that was not silver. We have to look up what is the isomorphous binary diagram. So silver cannot fully dissolve into copper. So here is the copper silver diagram. And you see, if we just try to combine them into whatever composition, and there's only one point, so neither pure copper or pure silver or any combination in between, but actually only this one. Why don't we just put 71.9% of silver into copper? If you create such a mixture, and at that point you can melt your mixture with the least temperature. Yeah, and this point is so-called eutectic point. Yeah, and this temperature here is so-called eutectic temperature. Yeah, that is the name of this eutectic system. That's why we call it when a system is having this kind of eutectic feature is called binary eutectic system. All right, I hope that definition is now clear for all of you. Let me just try to now, oh, sorry about that, get rid of my drawing because they are kind of disturbing the next component. All right, and if you just try to visualize here, so we actually created 3 single phases for this kind of eutectic structures. It's a little bit more complicated than isomorphous. So we have the liquid, that is a solution, and we also have this so-called alpha. So this is a solid solution, and this beta is another solid solution. So anything in between will be mixture. So this is liquid mixture with the solid solution, and that is another. And here is a complete mixture of solid solutions. Yeah. So here we have to be clear: the silver cannot really be dissolved into copper, not completely, but actually it's just so little. Yeah, and the same applies to copper to silver. So that is the beta case. All right. Okay, I think the system or the specific point we need to kind of emphasize here is about this eutectic reaction. Yeah, because this point is having some unique feature. The unique feature means when you just cool down, if you have a specific composition of the copper and silver, if you just cool it down from the liquid, it will be completely dissolved to alpha and beta. So at this point, you will not go to a phase that will be a coexistence of liquid and solid. So you would directly go from solid liquid to 2 solid solutions or to a mixture. And that is the unique point. So the same applies, vice versa. If you just go back with a mixture of alpha beta and in such a combination, and you would directly go to liquid. This is the very unique point about eutectic reaction. So I hope everybody could get it. We will see it again in the following diagram. And there are a few, let's say, kind of features about this eutectic system. Now we're going to explore them one by one. We talk about the eutectic point. So that was something specific. But let's go, let's say we don't go to the eutectic point, we go a little bit smaller. Volume fraction, for example, here we're talking about 2% of tin into a lead system. So this is also a eutectic system. So it's a little bit different from the copper silver. And I'm not plotting the whole phase diagram. You can see we're stopping at 30% of tin. But you can imagine this is looking exactly similar to the copper silver system. And what will happen if we just take 2% of tin into the lead system and we just cool it down from really high temperature? So from 100 degrees C, what will happen? So first you can see the kind of microstructure is completely in a liquid solution, and when we just go to a temperature below the liquid use line, maybe you still remember this line here, and then the solid solutions of alpha start to generate, start to be created. And you probably know they're created like nuclei. Right after this part of the lecture, you will learn how these nuclei are created. But now you can imagine they're just created like small nuclei, small seeds. And when you just cool it down further, they start to grow and the liquid becomes completely solid, alpha. And this is how it happens when you just go with a small volume fraction of tin into your system. And of course, for the alpha beta in the range of this kind of 2% and to, let's say, that this somewhat 18.3%, the situation looks a little bit different. Let's say we still start with a rather high temperature with around about 400 degrees C, and we cool it down, and this is the same. And you could this completely alpha phase, right? This is everything is fine. But if you still cools down, as you can see here, you start to generate. You don't stay with the completely alpha solid solution. You start to generate the beta. So remember, beta is there. Yeah, beta is somewhat there. This is so-called beta. And here, if you just apply the lever rule, yeah, imagine you have the volume fraction here is, let's say, 100% of tin, and you're going to generate some beta. So the beta nuclei will be generated into your alpha solid solution, and finally, you're creating a mixture of this kind of two phases, right? And this is the kind of second part of the phase diagram. And now we go to a little bit specific point. So this is the eutectic point. So you know the eutectic reaction, but here I want to show you how the kind of microstructures will be developed for this eutectic point. So here again, we start from a high temperature and it's completely liquid. Now we go down. Yeah, if you just go down at this exactly eutectic composition, you will actually develop such a microstructure. So this one, so this kind of laminar microstructure. Yeah, this is a very unique feature about eutectic point, because you are not creating a liquid and solid solution like, you know, anything like here or there. You are directly going to from liquid to two solid solutions. So this is the unique feature of creating such a alternating or layered structure. Because if you remember, the phase transformation deep down is driven by diffusion, right? Remember this. So when you just diffuse, so when you come to this point, exactly at this eutectic point, your liquid solution will be decomposed into alpha and beta. So for alpha there, you have just so little tin, and for the beta, you have so little lead. Basically, this process is driven by diffusion of lead out of tin or tin out of lead, vice versa. So at one place, the lead is leaving the tin, and you're creating a beta phase, and at the same time, you're creating an alpha phase. And this process just happens, you know, alternatingly. And that's why you're creating such a layered structure. Now, this is a very unique point of this eutectic composition. Now I think you get it. And here I'm showing you figure how it looks like in a real microstructure, let's say microscope figure. So you see this black and white, they're representing the alpha and beta phase of your system. And if you just look closely, you would see how the diffusion is happening. So when your lead just leave the tin and it becomes the, let's say, the beta phase, when it go to the thing, it becomes the alpha phase. Yeah. All right, so that was the unique part of this eutectic point. Now you see we started about completely alpha here, and we started about something between 2% to 18%, and we started about this eutectic point, and what is left is basically this region. You can see it. So what would happen if we cool our material with such a composition? So between 18.3% to 61.9%. So this is the part, the microstructure becomes a little bit more complicated. Let's go with it. So first, as you know, we're gonna go to a liquid solid phase. So liquid plus alpha, you know what will happen. So the alpha, the solid solution will start to nucleate and they start to become a solid solution more and more, of course. And right before you enter the eutectic temperature. So here I'm illustrating you with a little bit gap right here, but actually just imagine you're right above the eutectic temperature. And what is the composition there? So you know the composition over there is exactly, you're gonna have the alpha kind of phase with 18.3% of tin right there. and you're gonna have the liquid, which is containing exactly eutectic composition. So 61.19 in your liquid phase. So remember, this is right before you enter the eutectic reaction. So over here, exactly with this number we're choosing here, and we're going to 50% each. Yeah. But if you just go below, so right below the eutectic point, because now you are starting the eutectic kind of reaction, and then suddenly your microstructure is doing some magic. Because when you just enter eutectic reaction, you are kind of generated alpha. So remember this cute, let's say alpha grains, and they will stay the same. But your liquid, so you have your liquid solution over there, and you have exactly eutectic composition for your liquid. And right below the temperature, your liquid will start to generate this kind of eutectic microstructure. So this kind of layered alternating microstructure with the alpha and beta. So exactly looking like this. So this is a very unique point or interesting point for this microstructure, for this kind of composition. You're between this 18.3% and the 61.9%. And the alpha and beta kind of consumption will be different at this point. So your alpha is still 18.3%, but your beta is becoming 97.8% of tin inside. And the kind of volume fraction will be also changed, because you have to use the lever rule again. And at this moment, your lever rule is starting from R here, and the S is directly going to your beta phase. And we're going to elaborate this a little bit more in the next kind of figure when we talk about the iron and carbon diagram. But remember, this is something unique. And we spoke about these 3 points, and we didn't speak about a composition right there, but you know the composition or the microstructure change over there will be similar to also the left-hand side. And now we want to give you a name about this kind of a unique part. So this part and also this part. So if we go to the left-hand side, yeah, and this part is so-called hypoeutectic region or hypoeutectic reaction. And you know, hypo means below. So this entire word basically means you're below the eutectic composition. So when you have your microstructure or composition below the eutectic composition, it is so-called hypoeutectic, and the microstructure will be creating you a eutectic composition or eutectic microstructure plus the so-called alpha. So this kind of alpha is so-called primary alpha, because they were created before you had the eutectic reaction. And exactly with the same method, if we go with the hyper, so if you go above your eutectic composition, and you're creating this so-called hypereutectic reaction or hypereutectic region, and hyper, you know, in Greek, so this is again Greek, yeah, means above, yeah, or over. So over here in the microstructure, you're having the so-called the beta, so primary beta phase in your microstructure. Okay, I think everybody is pretty clear with everything here. So you know the eutectic, and now we have something so-called hypoeutectic and hypereutectic. Yeah. All right, good. Now I think we're quite done with this so-called binary eutectic system, and now I'm just trying to introduce you something more complicated. So as I told you, we're getting more and more complicated, and here we are back to the copper and silver phase diagram. You see, it's more or less the same, and there are 2 terms I would like to first introduce you still with this phase diagram, and they are so-called the terminal solid solutions. So these are referring to this alpha and beta. So if you just look at this diagram, actually, if we say the 0% of silver in copper is 1 terminal, and 100% of silver is another terminal. Basically, when you come from one terminal to the other, right, you're trying to kind of change your composition. And this alpha and beta, they're so natural. So here's about 2%. Over there is also close to 2% or so. So they're kind of like this terminal solid solutions, because they're only possible when you have very close to copper or very close to silver. Yeah, they're so-called this terminal solid solutions. And you know, we have terminal solid solutions, then we have some intermediate solid solutions. It's like you're taking flight with a transfer. So this is a diagram I'm showing you with the copper and zinc system. So it is much more complicated. I'm not showing you the full diagram over there, but you can see the gamma here is the so-called terminal phase diagram and terminal solid solution. And then we have some kind of epsilon. So the epsilon is another terminal kind of solid solution. And you see in between, we have another solid solution. This is the so-called delta. Yeah? And this delta is so-called intermediate solid solution. And by introducing this kind of intermediate solid solution, actually we're creating something more complicated for our phase diagram. You probably already see just by a first glance, but here I'm going to tell you something in detail. Because for this beta, for this delta, sorry, if you just look at it, when we just try to go from low temperature to higher or high temperature to lower, you would say there's a new kind of reaction. Because if you just go from beta itself and you cool it down, delta, sorry, you cool it down, and actually this delta solid solution will be decomposed into two solid solutions. They're gamma and epsilon. Yeah, the reaction is written like this. Of course, if you can go backwards, you heat it up with a solid solution of gamma and epsilon. Of course, they have to be in a specific composition region, and it will become delta. So this is very similar to what we had with the eutectic point, right? Yeah, but what is different here is we're not becoming liquid. It's not really melting. It's kind of like melting. That's why we gave the word is so-called eutectoid. So oid in Greek is also having meaning. It means something like. Yeah. So it's a like melting, but it's not exactly melting, because you're putting two solid solutions or mixture kind of back into one, but not one liquid, but into one solid solution. Yeah, this is so-called eutectoid transformation. And if you just go forward, if you go just heat your kind of gamma phase, your delta phase more and more to even higher temperature, and actually the delta is becoming a liquid plus another solid solution. We had this many times, right? But we had it in a different way. We kind of, if we cool it down of your liquid, the liquid usually could become, you know, the two solids. This is exactly what we had with the eutectic. But here is a little bit different. So you cool down a liquid plus a solid, and it becomes one single solid. This is so-called peritectic transformation or peritectic solution. And you know, peri in Greek, it also has meaning. It means kind of around or near. So this is not exactly kind of tectic or to melt, but it's like peritectic. Yeah. All right. I think everybody got it. So now we get two new, let's say, transformations. One is eutectoid, one is peritectic. So now we're gonna use this basically to get a summary for you, because these three are the most important phase transformation, especially the first two. They're extremely important for us to learn many metallic microstructures. And the peritectic is a little bit less common, but you should also know them. So here I try to give you a summary here for eutectic. You know, it's basically we're cooling a liquid down and the liquid is becoming immediately two solids. Yeah. So one example is lead and tin phase diagram. Remember that. And eutectoid, yeah, is basically we're cooling down one solid phase, and this one solid phase will become two solid solutions immediately. And this is also giving one example we see before, like copper and zinc. But we're going to see this much more in detail with a iron and a carbon phase diagram. And the peritectic is something a little bit reverse. Yeah, that's why it's called peri. You're actually cooling down a solid with the liquid, and then it becomes a solid, right? And this is so-called peritectic. And one example is happening with the iron and carbon. Once again, I'm going to show you a little bit later. All right. I think that was basically all the so-called solid solutions, you know, the terminal, intermediate, and also the three reactions we introduce you. And here's the final specific case, final special one, and that is so-called intermediate compounds. So this is nothing but a intermediate solid solution. And what is unique about it is it just appears as a line in your phase diagram. So meaning if you have such a composition in your phase diagram, when you just cool it down or heat it up, this composition will not be becoming something else. It will just become solid, and when you heat up, it becomes liquid, and vice versa. It's basically like a single, let's say a single material, like you're doing your water. You cool it down, it becomes ice, and when you heat it up, it becomes water. But here we're kind of mixing it with two components, but actually it is behaving exactly like one material. And this is so-called intermetallic compounds. So you should know it's a specific kind of intermediate solid solution, because this kind of reaction here is specific, and we also gave a name, it's a congruent transformation. Yeah, basically means it stays as it is, doesn't change. All right, I think that was all terms or new ideas, new kind of names to introduce to you. And finally, here I'm trying to give you one example. This is so-called famous iron carbon phase diagram. And this is one of the most important diagrams, let's say from our material science engineering course. Remember, we were speaking about the kind of atomic structure, so crystal structure. That was one of the most important diagrams you learned as well. And then we stayed a lot with the stress strain curve. That's another diagram. And this guy is basically the third diagram for you really to keep into your memory. I know this is very complicated, so you don't have to remember all the details, especially all these numbers. Yeah, because you will be always able to kind of look it up. And what you should try to keep in mind is learn how to analyze this diagram. So now I'm going to show you one by one, because it's rather complicated. I will slow down a little bit so that you can fully understand. All right. First of all, I have to tell you, we are not showing you a full phase diagram, because the full iron and carbon phase diagram does not make sense. We don't try to put so much carbon into the iron, especially at the moment, you know, carbon is somehow guilty because we shouldn't use so much carbon. We should kind of eliminate carbon in a way. But actually carbon is so important in many, especially for steel making. It is really a hard job to do at the moment. But anyway, we're not really focusing on too much carbon into the iron. So we're stopping exactly at 6.7% of carbon in our iron system. And here, as you can see, this is something specific we just taught you. This is a so-called cementite. Basically, you're having 3 carbon atoms in corresponding to 1 iron atom. And this is a intermetallic compound, right? You recognize that, because it doesn't change its composition when you cool it down or heat it up. And in between, we have actually a few features. Let's start with counting the solids or solid or liquid, any solutions. So of course, first we have the liquid solution here. That is fine. That's complete liquid. And then if you just go with the temperature decreasing trend, we have the first solid solution is called this. So dirt is a dirt phase. And then we go down just besides it's kind of gamma. Gamma already has a specific name. Yeah, it's so-called austenite. Yeah. And by the way, this gamma is usually having a FCC structure. And there's something for you to recall. And then if we just go to the right-hand side, we will at the similar temperature find our so-called cementite. So this is the intermetallic compound. And then if we just cool down the temperature further, we're gonna have the so-called alpha phase. Maybe you remember here, this is the so-called alpha iron, and it also has a special name. It's called ferrite. Okay. Yeah, now maybe remember when we just don't want to specify you about iron, there's always a distinction between alpha iron or gamma iron because they're kind of referring to different microstructures or two different crystal structures. So these are basically the 5 solid or liquid solutions. So 5 solutions. And now we're gonna try to explore some unique points. I'm already telling you there are 2 important points. Actually, there are 3, but the third one is not that common to visit. I will tell you which one is it. Let's look at the 2 important points first. Maybe you already recognize. The first one is this point A. It is a eutectic point, because your liquid is directly becoming at that point 2 solids. So your gamma phase plus your so-called cementite, right? And the second point is this point B. That is a so-called eutectoid point. Yeah, exactly. And the corresponding composition is 0.76 carbon in your iron. And at that point, your gamma as a solid solution will be directly decomposed into 2 solid solutions, alpha and also cementite. Right? And here I'm showing you how it looks like. So you know how the eutectic phase looks like. That it would develop it such as a alternating microstructure, with alpha and with gamma and cementite. And the eutectoid is basically exactly the same as eutectic. You're gonna also developing this kind of microstructure, basically alternating layers about your cementite and also your ferrite. Something to be just noted is the cementite is a really hard phase or hard intermetallic compounds. And the reason is simple because you have a lot of carbon there. Maybe remember the first kind of strengthening mechanism we were speaking about last 2 weeks ago. Right? Strengthening material is basically by what? By solid solutioning. Basically just dissolve carbons or any other atoms into your mattress, into your FCC BCC microstructure. That will basically change the stress field of your dislocations, and that will make your material harder. And that's why when you have more and more carbon, your material actually is harder and harder. And the ferrite, as you can see, on the other hand, have so little ferrite, has so little carbon atoms over there. That's why it's much softer. And now you get the microstructure, and you also see in reality how it looks like. It's really just kind of a laminate structure with these layers augmenting each other. All right, good. Once again, as we did with the binary eutectic system, now we're going to do something more complicated here because we introduce you the eutectoid reaction, and there will be something specific for the eutectoid composition. And you can imagine already the specific part is this hypo-eutectoid part. And this is exactly corresponding to the eutectoid composition and to the maximum solubility of your gamma phase. So if you just count number, the eutectoid composition is 0.76%, of carbon, and for the most solubility of carbon in your alpha phase is 0.02%. Yeah, you don't have to remember this, but just try to see them because they matter a little bit when you try to read a chemical composition of your steel in the future, not now. All right, let's see, when we have such a composition in our materials, what will happen? And let's just look at it. We will not start from liquid phase anymore because you know what is exactly going on there. So we directly start with the austenite. Yeah. And when we have the austenite as a solid solution, so they're looking like, you know, cute grains. And when you just go further exactly at this kind of solidase line, you know, the kind of gamma will be decomposited because at the moment you will generate what? At this point, you will generate basically alpha out of not out of liquid, but out of your gamma solid solution, right? But the mechanism is exactly the same. You will have some seeds, you will have some nucleus, exactly this small particles, and it will start to grow, yeah, bigger and bigger. So when you enter the temperature right above your eutectoid temperature, this temperature is also pretty specific. It's 727. And you're gonna start with your eutectoid reaction, right? So your gamma will be decomposited into the alpha and cementite. And what will happen? It's exactly similar to what you had with the eutectic or hypoeutectic reaction. So the alpha, so initially generated alpha phase will stay as they were, and they don't change anymore, but the gamma phase will be just decomposited into this kind of layered structure, alternating layer structure, looking like that. And then they will start basically, you know, the further diffusion if you go to other temperatures. And in the reality, you can see this is how it looks like. So the white basically is the alpha, the so-called primary alpha. That is how we call it in a eutectic phase. And for a eutectoid, we call it pro-eutectoid ferrite. You can also simply call it ferrite later on. Just to be more specific, this white is so-called pro-eutectoid ferrite. So maybe you know pro means basically before. And the kind of dark or layered structure is so-called a pearlite. So they are exactly not a, let's say, a solid solution, to be more specific. They're a mixture because they're a mixture of alpha and your cementite, right? The black is cementite and the white is alpha. But because they're so unique and the microstructure here is so fine, we even gave them a name. They're so-called pearlite. So remember, pearlite is not a solid solution. Pearlite is a mixture. It's a mixture of two phases, alpha and cementite. But because they're so, let's say, fine microstructure and they're so common, we gave a name and we even called them a phase. So pearlite, you will often see, what is your phase? It's pearlite. Yeah, is it a phase? To be more specific, well, it's a little bit like phase, because if you just look at pearlite, your pearlite region here, they're the same basically as the region there. So they're more or less explaining a, let's say, a common or the same chemical or mechanical property. But if you just zoom in, yeah, if you zoom in and in, when you just compare the alpha and the cementite, they're obviously not the same phase, right? And so this is the tricky part. You should recognize pearlite as a phase just for our engineering application, for our definition of material science. But in terms of the more specific definition, you should remember pearlite is a mixture. It is not one single solid solution. It is a mixture of alpha phase and cementite. All right, I hope that was clear. And let's go further. And here, I already told you what is the kind of, let's say, composition, or what is the kind of pearlite and looking like and how it is distinguished from the other. Now we want to talk about the composition and the fraction of your microstructure, because this is the part that is getting a little bit hard, and you should really pay attention at the moment, because it could be really kind of confusing if you don't pay attention right here. We will just explain you why. So right here, let's say when you just go to the temperature right above your eutectic temperature, you see we have alpha, so the pro-eutectic ferrite. We just simply call it ferrite right now, right? Ferrite over there, and you have the kind of fraction of your ferrite with this kind of small s, small r and s. Just by compiling the ladder rule, you will determine your fraction of alpha by s over r plus s, and that was simple. And the fraction of gamma is just exactly 1 minus that. But when you just go further, when you go to exactly the temperature below or right below your eutectoid temperature, this is the part you're going to generate your perlite. So perlite, you know what it is, right? The alternating layers of alpha and cementite. And how do you calculate your volume fraction over there? And you're going to use the capital R and capital S, right? So here I want to calculate what is the volume fraction of my alpha, of my ferrite. Guys, pay attention right here. Because if you want to calculate that by applying the new ladder rule, you will use the capital S divided by the capital R plus S. So as you can see here, you're going to have a lot of ferrite, right? And the important message here, the ferrite here, this kind of alpha phase, is a sum, yeah, of your ferrite, or to be more specific, of your pro-eutectoid ferrite alpha plus the ferrite in your perlite. Yeah, this is the key point. I hope everybody got it. Yeah, and then of course, if you just apply 1 minus that, you got the volume fraction of your cementites. Yeah, but if you just look at your microstructure here, actually the key feature or features that engineers want to know is the volume fraction of my pro-eutectoid ferrite and the volume fraction of my perlite, because we consider, remember, perlite as one single phase. Yes, we want to know the volume fraction of cementite, but we want to know more what is volume fraction of perlite, or what the volume fraction of the ferrite. Yeah. So you cannot use this rule anymore. If you just say, I'm going to apply this capital R and S, I'm telling you, okay, my ferrite volume fraction is capital S over R plus S. That is wrong, yeah, because that is the sum of your ferrite. And so here the key point is for you to realize the perlite volume fraction is this equation. The perlite volume fraction is exactly equal to the volume fraction of your gamma phase, of your austenite, before it enters to the eutectoid reaction, right? This perlite fraction is exactly the same as this one. And the ferrite volume fraction, or the pro-eutectic ferrite volume fraction, should be calculated by this equation, not the capital S and capital R. All right. So I hope that is clear. And we were speaking about hypoeutectoid steel. And I can tell you, this part is the most important applied steel. We actually very seldomly go to a carbon composition more than 0.76. That is very rare to use a composition of carbon more than that. So that's why we paid really some time and effort to get you through about this part. And of course, you have the opposite. This is so-called hypereutectoid, and this is rather, let's say, just opposite. I would just give you a rather quick kind of slide. As you can see here, we're gonna have some cementite, primary cementite generated, and when you just enter the eutectoid reaction, right, you're gonna have your perlite again, and this is a composition about the eutectoid steel. All right, so that is how you can also do the calculation about the composition. So I'm going to go a little bit faster here, and just make sure you pay attention about these numbers. I said you don't need to memorize those numbers, but the numbers will be a little bit important because we were only speaking about ferrite, iron and carbon. And you should remember when you just go to your work in the future, you might see some different numbers. So why they're different? Because when you just add any other alloying elements, for example, titanium or chromium, this is a very important alignment we need to speak about. Well, we need some stainless steel, right? The eutectoid temperature will be changed. Yeah? So remember, the pure eutectic temperature, eutectoid temperature is about 727, but when you just add more chromium, the temperature will be raised. And at the same time, the composition of your eutectoid composition will be also different. So when you just add chromium once again, so your eutectoid composition will be get kind of increased as well. All right. So here it's good time for us to get a summary about all the phase diagrams. And let's say I basically introduce you the phase diagrams, and the definition about phase diagram is a tool to basically let you know what is the temperature, what is the chemical composition of your material at a certain temperature, right? And you should be able to know the number and types of phases presented. From the phase diagram, you could also know the composition of each phase, and you should be also able to know the weight fraction of each phase. So this is basically all the information you could get from phase diagram. And we also introduce you some important reactions of phase transformations. They're basically eutectic, eutectoid, and pereutectic reactions. And finally, you should know the microstructure of your material depend really on the composition, yeah, especially when you have a hard phase and soft phase, right? And most importantly, actually, the microstructure or the mechanical property, basically the final phase will be determined by the cooling rate. We didn't speak about that. So we only say when we have a equilibrium, what will be happening? We would have this phase, we would have that phase. But I didn't tell you how much time we're gonna reach the equilibrium and how we should reach the equilibrium, right? So basically that will be our topic for the next 45 minutes or so in today's lecture. It's about phase transformation. It is dealing exactly the time. So I think now it's a good time for us to have a break, and we'll be back at 11:15. All right. Really work. And there was a nice question by Victor. Oh, sorry, Victor, you're the Victor with K. About the delta phase. I didn't manage to tell you during the phase diagram, but I think that was really nice question. And you probably got my answer. And that was exactly a place you could have some pereutectic reaction. Yeah. Now we will try to go forward with our lecture today about phase transformation. And now let me get my presentation open. It is taking a little bit time, but now it's open. Awesome. And here it is. All right, so this is finally the last item before we can really speak about let's say, processes. Because actually, after you get knowledge about phase transformation, and everything is done. So first of all, what is about phase transformation? Before we go to, let's say, this kind of solid phase transformation with carbon and iron, I just want to give you an analogy again. So we really always try to give you some analogy that you could correlate everything back to your life. So we kind of put everything for our study here about diffusion, phase diagram, and here now about phase transformation into a very good daily example, which is you kind of make your coffee. So you make your coffee with sugar or milk. Let's say you make your coffee with sugar. We were speaking about why, you could have your sugar into your coffee, because there's diffusion, right? And then we also said, all right, how much kind of sugar I can put there. So if I put a lot of sugar, what will happen? Do I still have a nice coffee with the sugar inside, or you would actually develop a kind of mixture? So basically your coffee with the sugar as a kind of liquid solution, and some sugar that cannot really dissolve as a kind of solid phase, right? And if we just go with different temperature, if this kind of different phases or the solubility of my sugar into my coffee will be different or not. So that was something about phase diagram. Of course, we learned much more than just the sugar into coffee, but the idea was same. Basically, that was to answer your question, like if I want to just have, the most kind of sugar in my coffee, how much should I put? If I put more, what will happen? The phase diagram basically could tell you at a certain temperature what kind of composition you will have, how many phases you will have, and so on. But what we didn't answer to the coffee sugar issue was, how much time do you need to get your coffee ready with a nice kind of dissolved sugar inside a uniform one? Not, at the end it's so sweet. I think a lot of people had this kind of experience. Your sugar wasn't completely there. When you just reach the bottom of your coffee, you found, that's why my coffee wasn't sweet enough, because all the sugar were on bottom, and they were staying there as a nice single phase as sugar itself. There could be two reasons. The first reason is you really reach the solubility of your sugar into the coffee. That could be the case. And the second reason actually is related to time. Remember, diffusion is a process that needs two things. Remember, one is temperature, and the second is time. If you don't just kind of diffuse your sugar enough into the coffee, you probably will not get your nice unique solution over there. And this is exactly what we're going to talk about for this concept. So the final thing, how much time do I need really to get a phase transformation done? As you can see, for let's say sugar coffee, that was easy. You could guess about how much time you're gonna need, and maybe you can even accelerate it with some spoon and disturbing over there. Maybe you should remember what is you're changing based on the diffusion mechanism. But if we speak about our solid solution, so solid phase transformation, so it's actually same thing. Because basically when we just look at here, this is something you just learned. This is a tectoid transformation. Basically your gamma phase, austenite, is transforming to two solid phases. One is alpha, the other is cementide, right? And what is deep down happening? Deep down happening is this kind of carbon atoms. They are just uniformly distributed into your FCC microstructure of iron. And when you just go to a lower temperature and you're experiencing a eutectoid transformation, basically this kind of carbon atoms, they will be going to a specific place with a lot of them. So this is what you have with cementide, because cementide is basically accumulating carbons with something like, remember, 6.7%. But when you just go, the carbons go to this place and they will leave the carbon a little bit much less in other places. That will become your ferrite, because ferrite, maybe remember, the most solubility of ferrite of carbon is 0.02%. So this is what happening. So the carbon atoms are just moving towards a place and they're leaving out towards another place. And this is the mechanism. So we basically want to know how much time does this carbon atoms need to transform from one place to another, and then we can reach a finally equilibrium state, right? So this is the basic question we need, and the kind of expanding question is, what is rate of it? What is rate for us to get the gamma phase finally into these two phases? So basically the perlite phase. And if we don't reach then the equilibrium phase, so we don't have the time to finally get this equilibrium phase, what will happen? What will happen if it's a non-equilibrium phase? And the last point is really finally trying to get the microstructure or this kind of phase transformation back to our microstructure and also to the properties. So when you have kind of equilibrium phase transformation, what is the microstructure looking like, and what is the property will be looking like? And when you have non-equilibrium phase transformation, what kind of microstructure you're producing and what kind of mechanical properties are corresponding to that. All right, so this is basically the key kind of message of our second half of today's lecture. And here I'm giving you certain learning objectives once again. So there are really terms that you don't know yet, but you will know after, let's say, half an hour or so. So the first point is, how could we make a schematic drawing of transformation versus time plot? And this is already a quantitative kind of description, because we want to know the time. We don't want to know roughly. We want to know really in a good accuracy. And that's why you're going to need some equations for that, right? So first, we're going to introduce that equation. Basically tells you how much time for you to reach your phase transformation, complete or half or so. And the second point is, after you do this different kind of transformation, you'll be able to see what kind of microstructure you're going to create. So you're going to create some fine perlite, coarse perlite, bainite, martensite, and tempered martensite. So you know nothing about them except for perlite. You will learn each of them. These are microstructures that are created by different kind of ways of phase transformation. And thirdly, you're going to finally be able to correlate your mechanical properties when you have all these different types of microstructures. And the last point is a kind of systematic tool for you to basically look up or determine how much time you're going to need for you to get a certain phase transformation done. So for phase diagram, you know what your kind of phases will be existing when you have equilibrium, and this kind of the final diagram, we call it either TTT or CCT diagram. So the TTT refers to isothermal transformation diagram, basically tells you how much time you're going to get those equilibrium phases. All right, so 4 basic ideas, and now we're going to go one by one. So first is about definition of phase transformation. We actually already spoke a few times about it. So when we start to speak, when we cool our material down from high temperature to low temperature, basically liquid to solid, what is happening? And I always tell you, so first, when you have liquid, then you're going to have this cute nuclei, or nucleation points, or call it seeds, and then they start to grow and finally become a solid. This is exactly the process of phase transformation. What you need to know is the phase transformation is composited basically into 2. One is nucleation and one is growth. So basically your solid need to be nucleate first, and then they're going to grow. This is easy, but actually the kind of driving force and the kind of equations to control all this is pretty complicated. You will kind of learn them probably at your thermodynamics course. And if you don't reach there, you probably will get it if you go with the microstructure and material science engineering major, you go to your master program. You will learn much more in detail. So what is the driving force? Because this is related really to the entropy, enthalpy, and about the potentials of all this chemical composition. So we're not touching all the details over there, but we're giving you a kind of sense of it. The sense of it is the driving force is related to the delta T. So this is something you could already, you're applying basically in your daily life. For example, you want to cool down your water to some ice. You will not put your water into exactly 0 degrees C, right? Because that will really take some time for you to get your water completely becoming solid ice. You're going to put it into your refrigerator, right? Then the temperature in your refrigerator is minus 18 or minus 20, something like that. And just after some minutes or hours, you're going to get a complete ice. Yeah, and that is exactly the sense of it. So if we want to kind of accelerate, or we want to get our nucleation and growth of solid transformation happening, we should have a supercooling, yeah, or vice versa. If you want to become your solid to liquid really faster, you should go some so-called superheating. I think everybody is get there, but something you should get the sense in addition is when you just apply, let's say, a little bit of supercooling. Yeah, this is something related to the nucleation. When you have small supercooling, you will not be able to generate so many nuclei. Yeah, you will just generate a few and they will just grow. The consequence of that is you're going to have large crystals or large grains, right? And on the contrary, if you apply really large supercooling, so you have a lot of delta T there, and that is going to really get many nuclei happening. That is kind of relating a rapid nucleation rate. And with this many nuclei in your microstructure, what you know is you're going to have a small crystal or small grains, right? Because you have too many, and when they just grow, they're going to meet each other, and then you're going to develop a so-called grain boundaries, and that's it. Yeah. And maybe if you are just receiving our message quite in a good order in previous courses, you could already imagine what small grains or what large grains are implying to you, as that will be correlated to your mechanical properties. Yeah, we will talk about a little bit later in today's course. And with this knowledge backing in your mind, you could already get kind of sense of the solidification process. Yeah, just imagine this is actually a process so-called casting. Yeah, maybe you know it, maybe you don't. We will talk about next week. So basically, imagine you have a kind of, let's say, mass container. It could be anything, and you just pour your liquid iron or liquid something into this container. What will happen? Yeah, so that is very high temperature, and here the container is rather low temperature. You will have your solidification process going on, and a typical behavior you could observe is at the wall place, so somewhere here. Yeah, you could actually have really small kind of grains and also equal exceed grains. Yeah, the reason for that is simple, because you're gonna have a rather large delta T over there, and then you will have many nuclei over there, and then finally they develop and they meet each other, become small and rather, let's say, uniform shape. But in the center of it, actually, you can imagine, yeah, the delta T is rather small, because the heat is going to go to the outside of the container. That's why we're developing large grains inside, and they're really looking like elongated or columnar grains. So they're having a completely different morphology than the walls. Yeah, this is directly related to this kind of dirty or the nucleation rate of the solidification case. And there are two different nucleation types you could already now imagine. So that is directly related to the diagram I showed you before. So the first one is so-called homogeneous nucleation. That is the case referring to the center of the material, because you're just getting your solid phase out of nowhere. So you have a liquid and suddenly you want to get some surface developed that is looking like a solid. Yeah, and if you want to get that nucleation progress fast, you need to really get a high supercooling temperature. So the dirty T is usually between 80 to 300 degrees C. Yeah, and that's why it is slow, and you need a lot of supercooling. And for the heterogeneous nucleation, why you have so many nuclei over there? Because when you just have some surfaces, when you have some, let's say, mold wall and impurities, anything that is already existing as a surface, so the kind of solidification surface can basically attach to it and start to get their surface. So this is energy related. Yeah, you definitely won't learn that when you just go to thermodynamics, but here you could already get the sense of it. When you have some already surfaces helping you to develop your nucleation surface, and that will become much easier. So this is so-called heterogeneous nucleation, and the supercooling temperature is really small. You just need something like 0.1 to 10 degrees C, and you would already develop very many nuclei for this heterogeneous nucleation. All right, that was rather simple kind of description about mechanism. As I said, just get a sense of it. You know, yeah, why you are having supercooling, superheating based to help the transformation process. And you also know there are two types of nucleation mechanisms. One is homogeneous, one is heterogeneous. That is good enough. If you want to look for some equations to help you understand this processes, you're going to definitely go to thermodynamics, either bachelor or even master courses to know much more. And now we want to know, because the final aim is we want to know the time. Yeah, we don't care how fast your nuclei are there. We just want to know how much time I need. Finally, I get a complete solid phase. Yeah, and here it comes to a equation that I can show you, because this is usually equation that we do via experiments. And that's why you're gonna need only a phenological equation to describe it. And here is it, because we need time. So the x-axis is time. What is unique here is we're using a logarithmic axis scale. So it's log time. And the y-axis is simple because we want to know, the extent of phase transformation, and that is the fraction of transformed phase. Yeah, if it is 0, there's nothing. Yeah, and if it is 1, that means your phase transformation is completed, right? Simple idea. So we typically would have a transformation shape or kind of transformation profile looking like exactly red one. So you start with the nucleation for really some time. So at that time, you kind of hard to describe your volume fraction of transformed phase. It's something, but it's hard to describe. It is really become obvious when you enter the growth phase. So then you can see some significant increase of your volume fraction. And here is the starting point. As you can see, if we try to describe the rate of it, the rate of the transformation, it starts with a rather small kind of rate, but then it goes faster and faster, right? And when you just go to a kind of middle point, more or less, and you reach the maximum rate of transformation. Yeah, so we're speaking about the rate and the slope of this curve. Because when you just go further, the transformation rate is going to slow down again, and until it reaches 0, which means your transformation is complete. That was simple. actually this kind of shape of curves is already not unfamiliar with you. You have seen a few types of this curves. Maybe from last exercise, you were even doing something like that, right? They kind of brittle ductile transformation, and you were using one equation to describe it. That was okay. And just last week, no, yesterday, yeah, we were describing also something similar. That was this kind of error function. Maybe you remember when we did describe the diffusion of the second Fick's law. Remember that? And that is also a similar shape. But here we're giving you, again, another equation. This was kind of invented by Mr. Remy. And there are also many more people kind of work on it. So we call it JMAK. So A is kind of represented by Mr. Remy. This is so-called JMAK equations. It's very simple. It's an exponential equation over here. And you only have your T as a x-axis and your y as volume fraction. And there are two perimeters. Oops, that is good. So you only have two parameters in the equation. The first one is K and the second one is N. So basically you're tuning these two kind of parameters to describe this phase transformation. Here, maybe I could do this, and that is nice. Here I can show you the influence of these two parameters. For example, if you just fix your K and you study the influence of N, basically they're showed here. So if you have a higher N, you could imagine your transformation kind of rate is much faster than if you have a lower N, right? So 2.9 is much bigger than 1.5. And if you just fix, let's once again fix your N, basically here we have both 2.9, and this was the initial 2.9 with the K parameter of 0.1. And the red one is with the parameter of 0.01. You can see the slope was changed a little bit, but was not as extreme as the N. So the N is changing your slope dramatically. So the key parameter basically is kind of shifting, of course, with a little change of slope as well, but more is kind of shifting your kind of transformation profile from left towards right. So it is increasing a little bit more time for the nucleation phase. All right, so this is a equation to describe the phase transformation rate or so, and we don't want to have a continuous value about it, so we want to have a number. So you see the rate is not a constant, so that's why if we want to just describe the rate of transformation, we're going to use a number defined here. It's going to be the rate exactly at the time you reach, let's say, the 50% of the transformation. So the time is t.5. So remember, the 0.5 is referring to a half of the volume fraction of your phase transformation. And if you just take the reciprocal of it, then you just take, you get the rate. Yeah. All right. Now that was the rate of transformation. And here I want to give you a little bit example. So we put it into action. Here we're speaking about the eutectoid transformation. And here, let's say we're going to go from, the eutect temperature is 727, but let's do some undercooling. And what will happen? You see, when we just do some undercooling, your pearlite will be basically growing, so this is your pearlite. So alpha and cementine, they will be just growing towards the direction. So here you can see how the carbon atoms are moving if they get clustered at the ferrite, cementine, sorry, and that will leave the space to become a ferrite. All right. And now if you just try different temperatures of supercooling, what will happen? This is exactly shown in this diagram. For example, if we say we cool down the temperature from 727 to 675, and this is the profile of your phase transformation of eutectoid transformation. Yeah, it takes around about, let's say, 1,000 seconds to get done. It's not super long, but still it's a little bit long. And we want to get it faster. So now we try 650. Oh, okay, that's good. Below 100 second. And if you go with the 600 degrees C, so large delta T, you can get your transformation done within 10 seconds. Yeah, that is the kind of power of supercooling, right? But what you need to remember, yeah, that was what I told you at the very beginning. If you have a lot of supercooling, yeah, remember what? You will have many nuclear points, and that will develop a fine pearlite. So relatively hard, right? Because the grain size is smaller. But when you just go with a higher temperature or a rather small supercooling, you're gonna get some coarse pearlite. So coarse means rather large pearlite, and that is gonna be relatively soft. Yeah, maybe remember, yeah, what is the reason about the soft and hard? The second hardening mechanism of our metallic materials. Yeah, the first is solid solution, and the second is what is grain refinement, right? All right. That was an example about eutectoid transformation. You know the power of supercooling, and finally, we want to get some tool to understand, to get a time easily from the transformation diagram. So we have this, and you can of course plot it with all the different temperatures. This is 675, and you have 650, and you have 600, looking like that. But imagine if you just try to explore this, you will be seeing thousands of curves. This is something we don't want, right? And we also don't want to read the time that is so complicated. We only care actually more or less the final point, not so much in between. So this kind of diagram is useful, but it is not so concise. That's why we're going to develop a diagram. So this is basically the fourth diagram I'm telling you, the so-called TTT diagram. So TTT diagram is also referred to isothermal transformation diagram. So TTT stands for transformation, temperature, and time. Yeah, so this is so-called TTT diagram. And this is very easily done because the input for this kind of diagram is exactly this kind of figures. If you just apply different extent of supercooling and you just mark, for example, here, I'm giving 675 supercooling directly starting here. I'm gonna hold this temperature to see, observe how the transformation is doing. So this is why it's called isothermal, because it's a constant temperature. And you can see when you just hold a while, your transformation to pearlite is starting. Yeah, so before that, that is unstable, that is nucleation phase, remember, right? And at a certain extent, you develop 50% of your kind of pearlite, and finally you develop kind of 100% of your pearlite. That means you're done. Yeah, you get the complete of your phase transformation. And if you just go to another temperature, we do the same, and you finally will connect all these 3 points into a curve, into 3 curves, let's say. And this is exactly what we want to have, because we want to know if we just apply different amount of supercooling, how much time. I just need to read, okay, that about 10 seconds, the transmission start, and about 100 seconds, the transmission is done. That's enough for me. I get it for the good sense. All right, these are some animations to show you. As you can see from this diagram, if we just go lower and lower, so that was 700 or so. If you go 600, the time is smaller. And if you go 500 or some plus, it's even getting smaller. But my question probably is, if you just go even lower, what will happen? Is this just go like this, yeah, even smaller, or actually you see there's already turning. Yeah? So that is not the case. Maybe you should ask, why is that? Okay, so this is some, let's say, microstructure evolution during the transformation, and you're pretty familiar with that. And that was eutectic point. eutectoid point. And now I try to give you some non-eutectoid compositions. Actually, it's pretty simple. Yeah, it's just adding another curve. So let's say if we start with a rather high carbon concentration, so 1.13, and what will happen? So actually nothing new, because here you basically gonna start with austenite. So this is austenite, and then for this curve, basically it is depicting the time that you needed to get your austenite plus a cementite, right? And this is rather fast, and that's why you just have a curve. So immediately you get this phase, austenite plus cementite, and then you enter this kind of pearlite transformation point. And here I'm telling you already what is happening if you just super cool your austenite further. So you go something like below 500 degrees C. As you can see, the curves are turning. Yeah, maybe you know, you try to think about why my pearlite cannot be really like that, faster and faster. This is the point related to the mechanism of phase transformation. As I told you, it is related to diffusion, and you know diffusion takes not only time, but also temperature, right? So that means when you have really low temperature, the diffusion cannot do that well. That's why you're gonna have to become something less beautiful as layered structure, and it is becoming something like elongated cementite. So it cannot go like the layers like so long, it becomes kind of disconnected and becoming elongated small cementite. And this is the so-called bainite microstructure. So bainite is a little bit unstable, let's say, kind of pearlite. You can imagine it in that way. Yeah, the morphology difference is just the cementite is not layer anymore. It's becoming a elongated particles. And another phase I would like to introduce you is if you just apply a even extreme supercooling. So I directly, not just to 500 or 400, I directly go to room temperature. So suddenly I go to room temperature. What would happen? So here you will not even be able to trigger bainite, because even for bainite, you still need to, the carbon can still diffuse a little bit. So it cannot diffuse like a whole. It has to be local, but when you just go even lower, the carbon cannot diffuse at all. Yeah, and this will develop another phase. This is completely unstable phase, let's say, and it's called a non-equilibrium phase. And this is so-called Morningside. First of all, let me tell you what is Morningside. So Morningside is having a different crystal structure even. So it's a BCT structure, so body center tetragonal structure. So it's exactly looking like these black ones. So it is taking 2 FCC unit cells. Basically, it is using the face atoms and 3, let's say, 6 face atoms and also 4 corner atoms, and becoming a new kind of unit cell. This is the BCT. So this is also body centered, but it's not a cube anymore. It's a tetragonal. Yeah, as you can see, this process is not happening by diffusion because the atoms do not need to change their positions. And it is just happening by the mechanical loading. So your atom is getting constructed from this Z direction and getting elongated from this X and Y direction. If you know the mechanics, maybe you could refer this to already. They're so-called pure share, right? So the Morningside transformation is exactly driven not by diffusion, yeah, but by sharing. Yeah, that's why you see it is a diffusionless transformation, and it only depends on the temperature. So you see they're horizontal lines. So time is irrelevant. If you just hit the right temperature, you'll get your Morningside. Yeah. So here is the 0% is so-called the Morningside starting temperature. Usually it's something a little bit above 200 degrees C. And then you have the 50, and then you have also the finishing Morningside temperature. Why it's not 100%? I will just tell you in the next slide. So here I gave you a little bit summary because we're really kind of attacking many different transformations. So when we just go with the slow cooling for our austenite, we're gonna go get the eutectoid reaction. So you get perlite. When you go really fast cooling, so even fast, so that you're directly going to a very low temperature, this is so-called quenching, so rapid cooling. You're gonna get martensite. And there are a few features about martensite. So martensite is a single phase, first of all. It is a phase, yeah, because it's, you know, it's a phase that it's a place that you can really find uniformly mechanical and chemical kind of properties. And it is with the BCT structure. So the kind of transformation was done by not diffusion, actually by sharing. So if you just think about what is sharing, sharing is so-called plastic deformation. And plastic deformation should ring a bell in your mind. That is related to the motion of dislocations, right? And that's why the martensite will have lots of dislocations inside, and lots of dislocations will return, give you some residue stresses. That's why the martensite will give you fine microstructure and also very hard, let's say, mechanical behavior. And there's one feature, there's always some cementine produced during the quenching. You see, there's always a little bit diffusion happening. That's why you also don't get the 100% of martensite. There's a little bit of cementine out there. So the martensite is really too hard and too high strength. That's why sometimes it is too brittle as well. We usually apply another process, which is called tempering. So tempering is nothing but apply a higher temperature of the martensite so that the martensite could go back to, or somewhat go back to, this so-called perlite phase, but they're not exactly like perlite. I will tell you one in a second. So that was the TTT diagram. That is diagram you should really keep in mind, but as you know, the TTT diagram is something hard to do because you have to hold the temperature. Actually, in reality, we rather go with a CCT, so continuous cooling transformation diagram, that is looking like this. So you just put your material at a, let's say, ambient temperature, so, and then the temperature will just go down, but the mechanism will be similar. So I will not discuss in detail. You just should know the kind of the curves will look a little bit different. So when you just see a temperature time diagram, you always ask, this is a TTT diagram or CCT diagram. That's good enough. So I promised to you, finally, we're gonna correlate, you know, all this process different microstructures with their mechanical properties finally. So here I'm giving you a kind of sense of it. So the first point is the influence of carbon content. Yeah, this is something you should be familiar with already, because this carbon content, you should get it. If we have more, it's harder. If you have less, it's exactly soft. Yeah, and here I'm giving you some examples. If you're talking about a hypoeutectoid steel, basically you have the perlite as medium strength and the soft ferrite. Basically here, if you look at their yield strength, tensile strength, and yield strength, the strength is exactly proportional to the volume fraction of your carbon, as well as the hardness. Yeah, if you go to the kind of hyper region, so this is hypo, this is hyper, it directly goes like that. But on the other hand, if we just talk about the elongation, so this is elongation, the blue one, and the impact energy, sharp impact energy. So they're basically going down, yeah, with the increase of your carbon content, because your material will become brittle and brittle when the strength is higher. So that was the carbon content, should be easy. And something more unique is about the microstructure features. So we're talking about the grain size, either fine perlite or coarse perlite. Yeah, this is also kind of simple. So when you have fine perlite, your strength or hardness will be higher, no matter it is in hypo or hyper. Yeah, so at hyper, it is even more dramatic. So the fine is really much higher than the coarse. And on the same time, the ductility is become worse, right? And because you would have the trade-off between the strength and ductility. So this is about fine and coarse. And we can also make a comparison between the fine perlite and martensite. So you know, martensite microstructure is even finer, but not only about that. And martensite has many other features, as I just described to you. That's why no matter it's hypo or hyper, your hardness of martensite is extremely high than the fine perlite. All right. And finally, we're talking about the tempered martensite. So this is how the tempered martensite looks like. Basically, it is a microstructure that has ferrite, and so these particles are your cementite. So they're not layered, they're not elongated, they're really becoming small particles. And that is the feature about this so-called tempered martensite, right? And with this tempering, when you just develop your tempered martensite, your strength is really becoming smaller and smaller. As you can see, initially, your fresh martensite is having a yield strength, tensile stress, about 1600 or 1800 megapascal. And when you just temper it, you're becoming something around 1000 megapascal. But what you improve significantly is your so-called kind of a reduced area or the ductility. So you get really a increase about that. So it's about a trade-off. Yeah. All right. So that was all the correlation between these 4 different phases to the mechanical properties. Here, I would like to give you a simple summary about it. So we started with austenite for everything. So we didn't really speak about austenite, their microstructure, because as you can see, austenite is not that stable at low temperature. But you remember, we also have many austenites steel, especially stainless steel. So that is the point you should think about, how you can stabilize your austenite and it becomes stable at room temperature. Yeah. But we're not talking about in this lecture for austenite. So first we spoke about perlite. So perlite, the morphology is alpha ferrite plus kind of cementite in a layered structure, right? And probably you have some pro-eutectoid ferrite as well. And if you just apply a moderate cooling, you're going to develop bainite. So bainite is basically the alpha plus some elongated cementite particles. If you just apply the even rapid cooling, so it's becoming a quenching, you're going to get some BCT martensite, which is not driven by diffusion, and it is driven by sharing. So if you just do a reheating about tempered martensite, I will tell you a little bit in detail next week. So how the reheating is done, you're going to finally get some so-called tempered martensite. The morphology is ferrite plus some very fine, let's say, cementite particles. And their mechanical properties are really just strength going upwards when you just increase your supercooling, increase your cooling rate, but the ductility is going downwards. Yeah. All right. I think that's all we have already talked about for today's lecture. Yeah, this is a list that you have learned already. So you learned for the phase transformation, there's one equation, so JMAK equation, to describe the phase transformation kinetics. And there are basically 2 kind of diagrams to give you a estimation about the time we need to get your phase transformation done. So they're either the isothermal transformation, TTD diagram, or the CCT diagram. And finally, you will learn these phases. I told you at the beginning, perlite, bainite, martensite, tempered martensite, and you could also correlate their mechanical properties with their morphology. I think that's all about today's lecture. I'm sorry it goes a little bit later than expected due to some problems with my equipment. But here is the final announcements. Probably you didn't hear it at the beginning of this week, but here I gave you some summary again. So first of all, the book related to our content is 5, 9, 10. So these are the chapters you could refer to. And the usual deadline for an assignment is 6 p.m. Sunday. Something different is the QA time is basically merged with exercise on Thursday, because on the exercise session, we're gonna cancel basically the computational training. So for the week 4 and 5, yeah. So with that, you could really focus on the textbook related content, and that it will help you with the working load. But for the guys that really love computational exercise and so on, don't be disappointed. You will still have the slides and videos provided there. You could follow them if you want. The only thing is you don't get an assignment anymore about this computational side. But if you still would like to do some assignments, also don't be disappointed, because we're gonna have the case studies open, or they're already open. So you could really start doing that, and you will get even extra points for doing that. All right, I think that's all. And if you have any questions, definitely
I have a
go.
question.
Yeah, sure, go ahead.
So, did you say that there won't be any computational assignments for this week, or for the remaining, like for the whole of the remainder of the course?
For week 4 and 5, we will not have computational training. For week 6, we initially didn't plan for computational training. So simply saying you will not have computational assignments for the remaining of the lecture.
So for week 6 as well?
For week 6 as well. So you will
Okay.
not have the assignments, right? You would still have the possibility to follow some training materials if you're kind of fond of it.
I see, thank you.
No problem. All right. Any more questions?
I also had a question. So since the computation exercise is optional now, so if we do the computation exercise now, will we get points for them, or are they simply just completely optional now?
The assignments will not contain computational assignments anymore.
Okay.
Yeah. If you still would like to do the assignments on computational side, now go to the case study. Yeah, you will get extra points over there.
I'm sorry. So you mean that computational exercise is the exercise given in the exercise section, right?
Yeah. Any more questions? So if you are still confused a little bit, I feel like some people didn't really join maybe at the beginning of yesterday's course, or you didn't pay attention to it. And that is okay. Just to go to the exercise session tomorrow, no, day after tomorrow, you will learn even more details about this change, because the main goal is basically to lower your workload, because from the feedback that you gave, we felt that was a little bit over your limit. And because many of you, I mean, there are many of you are really adapting so well and trying to follow everything, and they even enjoyed the computation assignments. But for also a majority, or let's say a half or so of you, really suffered from this workload. That's why we're going to go with an optional way for the computational assignments or a computational training. So you still get training, but now assignments do not take any computational tasks anymore. Yeah. So if you want to do any computational related tasks, just go to the case study. Yeah, over there you are still given the chance to do it, and you will be able to collect points as well. I hope that's clearer for all of you. If you still have questions, don't hesitate to ask. But as I said, you could also visit the exercise session and you will get a more detailed overview over there as well. Okay, so it seems everybody's happy. And if you still have questions, as I said, don't hesitate to ask. And for those who are happy, and I wish you a good week and see you next week. Oh, did I miss some question from the chat? Where's the chat? Oh, here it is. No, that was wrong. Is Nice still there? He's still here.
Yes, I'm here.
Yeah, I just saw your comment in chat. You still have assignments, yeah? You just don't have the assignments with the computational tasks anymore.
Ah, I see. I understood. Thank you.
You got it?
Yes.
Yeah. So the regular assignments are still the same, but the assignments do not take any computational tasks. Yeah, because that is the point that people really struggle quite a lot and spend a lot of time. So now we try to remove that or make that optional for all of you. Okay.
Thank you.
Yeah, no problem. All right, then everybody enjoy the week and see you next week. And Wen Qian Rongfei, thank you for the course. See you next week too.